A tensile and bending stress tester that can be made at home. After posting the plastic welding videos, I decided I want to see how my method of welding held up in comparison with a couple different common methods for attaching plastic pieces together. Let's try to get Project Farm with it. I am conducting this test to learn which method of binding the plastic pieces has the highest strength, and even if there may be a best use case for different methods. It would be awesome to create some stress-strain curves for the connection. Yield stress can be found with those curves, and yield stress is the primary material characteristic used in engineering. The interfaces are kind of obvious. The stress tester is applying a load to the specimen, and the extensometer needs to attach to the specimen to measure the change in length. Now let's run through the plan to gather this data. The most costly instrument I need for this experiment is an extensometer. If you think about it, an analog extensometer is really just a pair of calipers clamped to the specimen to be tested under a tensile load. So why not just print up some little jaws that could be attached to my calipers? It is certainly cheaper than using anything I could find on the internet. So I did just that. These clamps just slide onto the caliper jaws and can be tightened on via a couple of screws. Make sure that the calipers are fully unlocked and it's ready to go. We're going to test 3 of each of the different attachment methods and average the results. I will have to enter the data into Google Sheets manually by watching the footage back for each run, then plot the 3 runs and average them from each attachment type to visualize the results. With that, I can use the 0.1% method to find the yield strength of each attachment type, then compare them. Let's get to testing. I created my own welding coupons that are 3/16 of an inch wide and 1/8 of an inch thick at the attachment point. The attachment point is so small because I only have 500 pounds of force at my disposal. That is not a lot in the material testing world. I made some clamps that attach to the coupons, and the caliper attachment bolts to the clamps. Pass the shackle pins through the 3/8 inch holes, and we're ready to test. Here are the coupons that I will be testing: 3 Gorilla Hot Glue, 3 JB Weld Plastic Weld, and 3 welded. The hot glue acted as expected. It didn't take a lot of load for it to yield, and there was a good amount of deflection before it failed. That's interesting. Surprisingly, the JB Weld Plastic Weld was a disappointment. I expected the epoxy to be of a strength that is between the Gorilla Hot Glue and the PETG. However, the adhesive strength was very low. My makeshift extensometer for some reason did not operate as expected, but I was able to still find the yield stress by watching the video back for 2 runs. It was also very difficult to handle the coupons without damaging the bond. The first specimen ended up breaking as I was setting it up. The plastic welded coupons also didn't fail in predictable ways, but not such that negatively impacts the strength of the welds. The first one failed in such a way that the individual strands broke apart. As you can see, the 3D printed part actually failed itself. The weld appears to be the strongest point. Keep in mind, I did print this solid. Interesting. And by this, I mean I printed everything solid, including the test specimen. Looks like a little dragon. The second run had a plastic deformation that I would expect, but the last one was really strange. It broke like a brittle fracture, meaning there was no visible deflection, and it failed suddenly with a flat fracture perpendicular to the load path. Very unexpected for PETG. Whoa. That being said, it didn't fail at a load way higher or lower than the overture's rated yield strength. Speaking of yield strength, let's check out the compiled results. This is how I gathered the data. I watched the footage back and decided to record a data point at intervals that showed either a reasonable change in load or extension. Using the loading and the elongation, I could calculate the stress and strain. Then I could average the stress and strain values. Now let's get to those plots that we've been waiting for. I wasn't able to create a stress strain curve for the JB Weld plastic weld since it failed before I could get a change in length measurement, but I did estimate the yield stress based on visual indication. However, the yield stresses were very different between the two runs. The first run yielded at about 259 psi, while the second at 470 psi, averaging about 364 psi, but I have zero confidence in that result. The Gorilla Hot Glue ended up with the stress strain curves that are relatively flat and difficult to assign a yield strength. It really acts more like a rubber band after about 10 pounds of force was applied, so I would presume you can call the yield stress at that point, which is about 420 psi. Normally, you're taught to use the 0.1% rule when determining the yield strength of a material. However, in this case, that method doesn't work due to the large amount of deformation in the plastic. Although, the yield strength can be simply seen by eye when it comes to the PETG welded coupons. Run 1 yielded at about 4,300 psi, Run 2, 4,500 psi, and Run 3 fractured at about 4,480 psi. The average of the three being about 4,427 psi, which is almost dead on Overture's rating for the PETG I used of 30.8 megapascals or 4,467 psi. So I can confirm that my welding method is at least as strong as the PETG part, but how did the welds hold up in a bending stress? The welded coupons held up perfectly while being bent. All the specimens bent in an area adjacent to the welded area and didn't fail. Thank you for watching. Please consider liking, commenting, and subscribing. Don't forget to share this video with anyone who might be interested, and thanks for sticking around. See you next Engineers Weekend.